What's up everyone? Welcome to this video on Keto-Enol Tautomerism, where I'll be covering the following. We'll firstly look into what Keto-Enol Tautomers are. Secondly, how tautomerism takes place under both acidic and basic conditions. And then finally, looking at the reactivity of enols with a specific example, which is alpha-halogenation of ketones. We'll then wrap up with a quick summary of what we've learned today. If you do enjoy this video and do find it useful, please click the like and subscribe button and feel free to leave a comment below. Keto-Enol Tautomers, so what are they? Tautomers are constitutional isomers, so different compounds with different structures, which are rapidly inconvertible. However, in this case we're specifically referring to carbonyl compounds. So if we take cyclohexanone on the left here, this then forms its enol tautomer on the right. So keto-enol tautomerism is just simply an equilibrium process that's established very rapidly. And as we can see, most of the carbonyl compounds exist almost exclusively in the keto form, and the enols are only present to a small extent at equilibrium. Although those enols are responsible for much of the chemistry because they are so reactive. However, in some rare instances we actually do see the enol form being dominant. So let's take acetylacetone for example, which of course has two carbonyl groups. We then see the enol being formed on the right, where one of the carbonyl groups is converted into an alcohol group with a carbon-carbon double bond. So the keto form on the left and the enol form on the right. And we do see only 14% in the keto form, with the majority being in the enol form. And this is actually down to two reasons. Firstly, we have stabilization by intramolecular hydrogen bonding over here. And secondly, we do have a conjugated system, in this case between the carbon-oxygen double bond and the carbon-carbon double bond, thus providing more stabilization. Now we know that tautomers exist, let's look into how tautomerism is catalyzed, firstly in acidic conditions. So we have our keto form over here with the lone pair on the oxygen, and we have an acid catalyst. In this instance I've used H3O+. So what we see is the carbonyl oxygen is protonated by the acid, which now gives us a cation, which will have two resonance forms. And just as a note, tautomers are different compounds with different structures, whilst resonance forms are different representations of a single structure. So the first resonance form has the positive charge on the oxygen, and the second resonance form has the positive charge on the carbon. And it's this second resonance form which we'll see actually loses the H+ from the alpha position by reaction with the water molecule, in this case acting as a base, which gives us our enol form. And alongside the enol form we have the regeneration of the H3O+ catalyst. So keto on the left and enol on the right. Now under basic conditions we actually see enol formulation occurring because the presence of a carbonyl group makes the hydrogens on the alpha carbon weakly acidic. So on this keto form over here, this is the alpha carbon. It's these hydrogens which are weakly acidic. And so as a result, a strong enough base can remove these acidic hydrogens, which will then give an enolate ion. So in this case, the hydroxyl ion will remove the hydrogen, and this will give an enolate ion with two resonance structures. So the first resonance structure with the negative charge on the carbon, and the second resonance structure with the negative charge on the oxygen. And I'll actually just show how those resonance structures are formed. So we have the formation of a double bond, which then breaks the carbon-oxygen bond, and then it's the protonation of the enolate ion on the oxygen, which gives us our enol. And it also regenerates the base catalyst. So we have a keto form on the left and the enol form on the right. We'll now look at a particularly common alpha substitution reaction, which is the alpha-halogenation of ketones in the presence of an acid catalyst. So firstly, we'll have our keto form, which, as we've seen earlier, in the presence of an acid catalyst gives us our enol form. Now, because the double bonds are electron rich, enols actually behave as nucleophiles and are effectively very reactive alkenes. So they react with electrophiles, in this case bromine, which now gives us a resonance stabilized carbocation with two resonance forms. So the first resonance form has the positive charge on the oxygen, and the second has the positive charge on the carbon. Now this second resonance form then loses the hydrogen proton which then reforms the carbonyl group, and the overall reaction is an alpha substitution. So we've replaced one of the hydrogens of the ketone with a bromide ion. So then, to summarize, what have we learned today? Firstly, we've seen that carbonyl compounds exist almost exclusively in the keto form. However, in some instances, for example with acetylacetone, the enol can be stabilized by conjugation and hydrogen bonding, which then means it's the more dominant form. We've then seen how tautomerism can take place under acidic and basic conditions. So in the presence of an acid catalyst, enol formation occurs firstly by protonation of the carbonyl oxygen atom, which gives us an intermediate cation, and this cation then loses a hydrogen atom from its alpha carbon to give a neutral enol. Under basic conditions, we've learned that formation occurs because the presence of a carbonyl group makes the hydrogens on the alpha carbon weakly acidic. Therefore, it can donate one of its hydrogens to a strong base. Subsequently, protonation of the resulting enolate ion then gives us the enol tautomer being formed. And lastly, we've looked at the reactivity of enols with a particular example, so the alpha-halogenation of ketones. So in the enol form, a carbonyl compound can undergo halogenation, which is a typical alpha substitution reaction. Thanks for watching.